You've spent months perfecting a new sunscreen formula, but after the final stability test, the emulsion breaks. The UV filters have succumbed to recrystallization. That one failure doesn't just cost you the materials, it costs you the entire development cycle. Traditional prototyping requires a manual cycle. You mix, you test, and you wait. When each iteration adds 3 weeks to the timeline, even a minor stability issue can push a product launch back by months. This chart compares those manual timelines against a digital, in silico formulation pipeline. By simulating the chemistry before mixing the first batch, labs are seeing their development time drop by 60 to 80%. But choosing a digital workflow isn't a single decision. The landscape for these tools is currently split across 7 distinct categories, ranging from free web portals to enterprise-grade software. The choice is high stakes. If you overinvest in software your lab doesn't have the compute power to run, you waste thousands on licensing. If you underinvest, you'll miss the molecular interactions that lead to clinical trial failures. Success in the 2026 market depends on matching your specific R&D bottleneck to the tier of digital tool designed to solve it. Let's look at the first scenario, a lab handling standard formulations on a limited budget, where the primary goal is ensuring basic filter solubility. For standard projects, the baseline tools are the BASF Sunscreen Simulator and DSM Sunscreen Optimizer. This scorecard tracks the macro baseline tier. These platforms are built on the O'Neill model, which calculates how irregular sunscreen films distribute across human skin. This model provides a 0.91 correlation coefficient between simulated results and in vivo tests. Beyond SPF, you get immediate data on regional UVA ratings, the specific volume of solvents required, and REACH-compliant eco-profiling. Both BASF and DSM provide access to these core simulation features without a subscription fee. However, there is a limitation. Relying on existing databases of known filter combinations, these platforms cannot predict the behavior of entirely new, untested molecules. These simulators provide a fast, accessible route to regulatory compliance, but they are not designed to analyze novel chemical interactions. To solve complex issues, you must look at the atomic level. Under light, UV filters can degrade or interact in ways invisible to macro simulators. This leads to the second scenario, a deep tech or academic lab that must prove the stability of a novel chemical complex or solve a persistent photoinstability issue. This is the Micromechanics tier. It utilizes molecular dynamics software like GROMACS or LAMMPS to track individual molecular trajectories. By monitoring these movements, researchers can predict the absorption maxima of active ingredients within 10 nanometers of precision. This allows you to visualize exactly how a UV filter inserts itself into a cyclodextrin cavity, providing physical evidence of how the molecule is being protected from degradation. This level of detail comes with a price. Commercial and academic licensing for these modeling tools ranges from 2,000 to nearly 11,000 euros per year. You also need significant compute power and specialized teams to interpret the data, since a 250 nanosecond simulation generates massive volumes of trajectory snapshots. This tier requires a higher investment in both capital and expertise, but it provides the atomic-level proof needed for patent-worthy chemical stability. In our third scenario, the base SPF is already established, but the goal is to secure high-end claims that appeal to premium consumers. Consider free radical protection. UV exposure generates reactive oxygen species that damage skin proteins, making radical neutralizing a major selling point for high-performance sunscreens. This scorecard tracks the tools for specific validation. For radical protection, researchers use CERN's GIANT4 DNA software to simulate and quantify radical damage on a millisecond scale. Then there is water resistance. Traditionally, verifying this meant an 80-minute human immersion test, where a single failure forces a total reformulation. Labs are now using spectrophotometric testers, a digital hardware hybrid, to scan skin substitutes before and after immersion. These systems cost between $2,000 and $8,000. This hardware produces results with up to 99.5% correlation to human clinical trials. These validation tools operate in specialized workflows, allowing you to secure premium claims without the financial risk of an unsuccessful human trial. The final scenario covers enterprise-scale ODM manufacturers who need to manage hundreds of high-speed product launches across different global markets. At this scale, the solution is generative AI platforms like Shiseido's Voyager or Hot.ai's SkinGPT. This scorecard tracks the highest tier of automation. These AI models utilize over 500,000 formulation data points and clinical results to predict how a recipe will perform, calculating the final SPF rating, viscosity, physical stability, and tactile texture. This changes the internal lab hierarchy. By relying on the AI's predictive history, junior researchers can develop commercially ready formulations with limited supervision. However, the capital required for this scale is significant. Implementation costs range from $2,700 for basic systems to over $274,000 for an enterprise multi-agent deployment. AI requires a large upfront investment, but it provides the speed and workflow delegation necessary for high-volume manufacturing. You cannot simply compare a free web calculator to enterprise AI or particle physics software. You have to map the tool to your R&D profile. This decision tree shows the path. If you are an indie brand or a budget-conscious lab using standard filters, prioritize the free BASF and DSM platforms. You get high macro accuracy for zero licensing cost. Your trade-off is the inability to analyze entirely new molecular structures. If you are a deep tech lab developing new actives, invest in molecular dynamics. You gain atomic proof of your stability, but you must account for high compute costs and a specialized staff. And if you are an enterprise OEM, you deploy AI and spectrophotometers. You trade a six-figure capital investment for maximum launch speed and the ability to delegate recipes to junior staff. No digital simulation will ever fully replace the final ISO clinical test, but choosing the right tool for your specific bottleneck ensures that when you finally pay for that clinical trial, you only have to do it once.